Agents need control flow, not vibes. This is the pattern you'll be able to implement by the end, which plans an allowed toolpath and executes it with a step cap to prevent loops. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Reliable agent control with state machines answers a clear pain. Agents with unrestricted calls wander, loop, or call the wrong tool. That wastes time and tokens and produces unsafe actions. State machines give you a predictable map. Success looks like a bounded sequence of tool calls, deterministic stops, and simple guards that block dangerous inputs. At its heart, a state machine routes a small state object through named steps. Each step can mutate the state, append a log, or signal a transition. The strengths are predictability and debuggability. The weakness is upfront design. You must decide the allowed paths. For many agent tasks, that trade-off is worth it. We will build a tiny guarded agent that plans, loops safely, enforces order, supports retries, and applies a safety gate. That concrete build proves the idea without a heavy framework. Now we'll create the minimal single-node machine. This snippet constructs a one-node LangGraph state machine and executes it. The function plan appends a simple note to the variable log so state changes are visible. A state graph is created with a plain dict state. Then plan is registered as a node and set as the entry point. An explicit edge to end ensures the graph stops after the first node, preventing accidental looping. The graph is compiled into G and invoked with a readable initial state containing text and an empty log. The printed steps value shows how many items were recorded in the log. The single recorded step confirms the workflow ran once and halted deterministically. Next, we'll add a bounded loop so the agent can repeat work a controlled number of times. This example adds a LangGraph conditional edge to bound a loop by state. The node act increments the counter n and appends a marker to the log so progress is observable. The function route inspects the current state and via add conditional edges sends control back to act while n is less than max. Otherwise, it returns end to stop the graph. The graph compiles to G and runs with an initial counter of 0 and a maximum of 3 iterations. Increasing max permits more passes. Decreasing it shortens the loop and reduces cost. The printed loops value confirms exactly 3 iterations executed before termination. Now we'll show how to force a strict sequence so tools run in the intended order. This code enforces tool order with explicit LangGraph edges. The variable order starts empty, and the node search appends its name to it so we can verify sequencing. A second node write appends its own name. Using add node and set entry point, the flow begins at search. Then add edge wires search to write, and finally write to end, making the path explicit and acyclic. The graph compiles and runs on a small state, accumulating the order of operations. The printed order OK value equals 1 when the sequence matches the intended search, then write, proving tools cannot be called out of order. Next, we'll add a retry pattern that gives a flaky tool a chance to succeed. This snippet adds a retry with cap pattern using LangGraph conditional routing. The node call simulates a flaky step that succeeds only after the first retry, by returning OK true when retries is at least 1. The function again looks at the updated state, and through add conditional edges, loops back to call while OK is false and the retry count is below max retry. Otherwise, it returns end to terminate decisively. The graph compiles and runs with an initial retries of 0 and a maximum of 2 attempts. Raising max retry permits more attempts. Lowering it fails sooner. The printed tries value shows exactly how many attempts were made. Finally, we'll attach a safety gate that blocks dangerous inputs before tools execute. This example implements a tiny guarded agent in LangGraph with a safety gate. The node plan is a placeholder that leaves state unchanged, while the function guard, plugged in with add conditional edges, inspects text and routes to run when safe or to end to block unsafe input. The run node simulates a tool call by adding 12.5 milliseconds to the variable ms so we can track latency. The graph compiles and executes on a benign price query, passing the guard and completing in one step. If text contained delete, the guard would end immediately. The printed latency milliseconds shows a small, measurable cost for the safe path. In a real integration, you replace the simulated run with your API call, and the MS counter with a timing metric. The guard becomes your policy check, and the log becomes an audit trail. The small state object scales. Add a user ID, request ID, and you get traceable, auditable agent runs. Recap. What it is: a state machine that routes a compact state through named nodes to make agent behavior deterministic. When to use it: whenever you want ordered tool calls, bounded loops, retries, or safety checks. One caveat: you must design the allowed graph upfront, or you trade flexibility for control. Next step: tune the retry cap parameter to balance success probability and cost. Increase max retry when tools are flaky and you can afford latency. Decrease it when you need strict cost control. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.